Okay, today we are going to discuss about the transmission line equations. How we can derive the transmission line equations. So, which is derived by using the transmission line equivalent circuit diagram. So, transmission line equivalent circuit diagram consists of the resistor, inductor, conductance, and capacitance. So, these are the primary constants of a transmission line, which are arranged like this. Now, which is arranged in a uh, direction of z, which is arranged in the direction of z axis. So this is one dash is the input port and two dash is the output port. Now, so here initial voltage is V of z comma t and initial current is I of z comma t. Now, which is the wave having this voltage and current, which is traveling from input port to the output port, that is two dash. So you can observe here the resistance R is multiplied with del Z. Why means R is measured in ohm per meter, but actual R will be obtained. So R is measured in ohm per meter. That is ohm per meter. Now here the del Z, the units for this del Z is meter length by multiplying with the del Z. The units are meter and both are cancelled. Finally, you are getting the original R value here. So to get the original impedance, we should multiply the L with del Z. To get the original conductance, multiply del Z. To get the original capacitance, multiply the del Z. So that is the meaning of multiplying the del Z for each and every constant. Now, output is 2 days. You can see one point, important point. So whenever we are transmitting the voltage from input port to the output port, so the output you may receive either equal to voltage or less than that voltage. Similarly, whenever you are passing the current from input port to the output port, so in the output you may receive the either equal current or less than that current you may receive at the output side. So that's why. So here the input voltage is I of z comma t and output is z plus del z. So that is the length of the transmission line, that is del z. And similarly, voltage is V of z plus del z comma t. So that is the transmission line. Now, based on this equivalent circuit diagram, we are deriving the transmission line equation. So to derive that, first apply the Kirchhoff voltage law in this loop. Kirchhoff voltage law in this loop. So what is Kirchhoff voltage? KVL will tell us the total voltages in any closed loop is equal to zero. So, so this is V of z comma t V because it is entering at the minus terminal. This is plus terminal. This is plus terminal. So this voltage is equal to voltage across the resistor and voltage across the inductor and the voltage between the two terminals. Voltage between the two terminals. So the voltage across this resistor is given by R into current I of z comma t. And voltage across the inductor is given by L into di by dt. Normally we are measuring voltage across the inductor is L into di by dt. So instead of L here we are writing the L into del z into di by dt or dou I by dou t plus voltage between the these two terminals. Voltage between these two terminals. What is the voltage between these two terminals? That is equal to the this voltage. This voltage. So this voltage. This is the equation obtained by applying the KVL in the input loop. Now transferring this into this side, you will get the minus V of z plus zt comma t. That is the second equation. Remaining as easily, I kept all the parameters here. Now, by taking the minus symbol common, this minus this, V of this minus this, and again divide the above equation with a del z on both sides. Then initially left hand side you are getting this, and right side this del z will be cancelled and this del z will be cancelled. Finally you are getting the r into I of z comma t plus L into dou I by dou t. So now apply limit del z tends to 0 on both sides. Both sides. Here there is no del z term in this side. That's why this limit is not applicable to here. As it is, the terms are like this, and but the the left hand side. So by applying the limit del z tends to 0, minus symbol as is. right side, this will become as this because there is no del z term in the right side. Now, so according to the definition of the differentiation, this will be equal to the dou v by dou t from the basic definition of the differentiation. Minus symbol as it is here, and remaining these terms are like this. This is the equation by applying the equation number 1, which is obtained by applying the Kirchhoff voltage law in the input front loop. Similarly, apply the Kirchhoff current law at this node. Kirchhoff current, KCL at this node. So what the KCL will explains, entering currents on a particular node is equal to the leaving currents. So what is the current which is entering in this node? I of z comma t, and leaving currents are this current and this current. So that is I have written here. You can see here. So I of z comma t is equal to I of z plus del z comma t plus del I. Then what is del I? That is the current which is flowing into the this conductance and this capacitance. Now we can express this del I in terms of the voltage. Now, so how can we measure this current flowing through this in the conductance? Voltage into this conductance, or voltage by resistance, or voltage into conductance. What is the voltage across this resistor? The same. This voltage across the. Why? Because it is parallel to these two terminals. In parallel, voltage is equal. That's why the voltage across this resistor is V of z comma del z plus del z comma t into G into del z, and again the voltage across capacitor we can find out by using the C into dou v by dou t. C means here C into del z, so that's why I have written here. So I have written, so instead of del I have written G into del z into V. This is the voltage into conductance becomes current, and again this is the voltage across the capacitor. Instead of C, we have written C into del Z. Why? Because it is a transmission line parameter. So dou V by dou T. Now, taking this I term into this left side, you will get I of Z comma T minus I of by, and again divide the above equation with del Z on both sides. You will get like this. You will get like this. Okay, so here in this case del z and del z will be cancelled because we have divided the above equation with del z both sides. That's why in the right side there is no del z term because it will be cancelled here. So again, by taking the minus symbol here, this term minus this term and del z, there is again the same term will be written here, and again apply the limit del z tends to 0 on both sides. On the right side there is no del z term is on the right side. That's why this limit is not applicable to the right side. That's why the same equation we have written here. In the left hand side we have applied the del z tends to 0. Now this will becomes the basic definition of the differentiation, that is dou I by dou t minus symbol as it is we have put in here, and dou I by dou t, and remaining these terms are written here. This is equation number 2, which is obtained by applying the KCL on the node. Now in terms of the time harmonics, so we can express the for equation number 1 as like this. So why? Because the differentiation will becomes j omega. One differentiation will become j omega. Two differentiation will become j omega whole square. Similarly, these two equations, second equation will becomes like this: g plus j omega c, and we have taken the VSS common. So now these two equations we obtained. So from this, now differentiate again this equation both sides with respect to z again. So we get dou square vs by dou z square, and again dou is by dou z. Dou z. This is dou z. Now what is dou is by dou z here? Minus of j omega g plus j omega c into vs. By putting here minus minus will becomes plus. So this is finally equation we obtained. So now this is the final equation we obtained. Okay. So now by taking this term into the left hand side, you will get the dou square vs by dou z square minus r plus j omega into g plus j omega c into vs equal to 0. Now, this is final equation. Now, by comparing the above equation with this term, here gamma square is called propagation constant, where gamma square is equal to r plus j omega into g plus j omega c, and gamma is called square root of r plus j omega into g plus j omega c. So here gamma is a propagation constant. We can express this in terms of the ignition constant and phase constant as alpha plus j beta. Similarly, for in terms of the current, the differential equation what you obtained is dou square S by dou Z square minus gamma square into S equal to 0. Same procedure we can apply here. So by solving the above two equations, you will get the final equations as Vs of this one. So you can see that this is the solution for the first this differential equation, and this next one is the solution. This is the solution for this differential equation. This differential equation. This is. So by seeing this differential equation, what we can understand is, so whenever the wave is traveling from the load generator to the load in a transmission line, there will be a wave which is traveling from positive z direction, and there will be a reflected wave which is traveling from the next minus z direction. Similarly, so whenever the wave is traveling in a transmission line, current also having two components. One is positive z direction current, and the minus negative z direction current will be close here. This is the final transmission line equation. Thank you.